Physicists observe natural phenomena, develop theories, and verify them by experiments. As they study, they work with several physical quantities like temperature, density, potential energy, kinetic energy, etc. Most of these quantities keep varying, but some always remain constant. In other words, they remain conserved. Conservation of physical quantities are based on well-defined laws of conservation. Two familiar examples are law of conservation of energy and law of conservation of momentum. If you ride your bicycle all the way to the top of a hill, you need to spend your energy. This energy gets stored up as potential energy in the bicycle. The moment you start coming down the hill, the potential energy starts getting converted into kinetic energy. When you reach the ground, all the potential energy is now converted into kinetic energy. Here, the total energy of the system at any point of time is given by the sum of all energies. One can observe here that the sum of these energies always remains constant. Law of conservation of energy. This law states that when one form of energy changes into another and vice versa, total energy in the system is always conserved. Let us see an example which proves this law. Conservation laws even help in understanding chemical reactions. In chemical reactions, atoms simply rearrange themselves to form products. No new atoms are created, neither are they being lost. Hence, the number of atoms involved in a chemical reaction remains the same on both the sides. Imagine a collision between a car and a truck. Though there may be many forces involved in the collision, we can work out the possible outcomes of the collision by using the law of conservation of momentum. Such estimation helps to prevent collision. Automobile industries use the law in manufacturing vehicles. There are numerous phenomena, beyond any length of human imagination, taking place in the universe involving changes in physical quantities. But still, amazingly, the total energy in the universe is considered to remain constant. Sometimes, old theories and laws are replaced by new ones, as more discoveries are made. For example, until Albert Einstein came up with his mass-energy relationship, E is equal to mc square, total mass of a system was considered to be constant, and this principle was explained to describe chemical reactions and endothermic and exothermic reactions. Einstein's mass-energy equivalence equation, which later paved the way for the production of nuclear energy, served as a breakthrough to the hitherto conventional line of thinking on conservation principles. Although laws of conservation which are applied in different systems can be the same, the quantities involved need not necessarily be the same. In most situations they do differ. For instance, universal law of gravitation. Force of attraction between two objects is directly proportional to their masses and inversely proportional to the square of the distance between them. Can be applied to different systems of objects, but the universal gravitational constant is the same, which is why it is known as universal gravitational constant G. Force of attraction differs from one system to another, depending upon objects' masses and the distance between them. For example, G force on the Earth is 9.8 meters per second square, whereas on the Moon it is only 1/6 of this value. Conservation laws have helped physicists in new discoveries. One such is the discovery of neutrino, an elementary particle emitted in beta decay reactions. Wolfgang Pauli predicted its emission by applying laws of conservation of energy and momentum. Conservation laws play an important role in explaining the symmetries of time and space in the universe. Physics helps us not only to explain natural phenomena and numerous processes, but also to apply physics concepts in problem solving in the classroom, laboratory, and the world around us.